Okay, first we need to start a new model and we need to define used constants that are absolute zero temperature and Steven Boltzmann constant. Okay, so then we need to create parts. Okay, here you have the choice. Either you create two parts that are going to be welded, or in this case, we create a single part, then we later going to create partition in this part. In this step, we're going to define and use materials. I've used stainless steel. The thermal and mechanical properties can be found in this research. Okay, now after adding the parts, now we need to adjust the direction for the parts to be along X. This is later important in defining the loads that are applied on the welding. Now we need to create the actual steps for the simulation. The first step is going to be the welding step, and it is about 50 seconds, and the second step 600 seconds. So, in creating interaction, you want to create interaction with the inert gas. In the case of, let's say, the TIG proceeding or the MIG-MAG proceeding, and also an interaction with the air or the temperature ambience, and the third interaction is going to be caused by the welding radiations. Now, in this step, we're going to apply the boundary conditions and the, the loads. In the case of the boundary conditions, we have simple no movement, no rotation in the sides of the place. So we're going to block any movement or rotations. And now we want to define the temperature ambience. It is set in the initial step is about 25 degrees Celsius. Now, before we go into loads, and we want to apply the meshing, and before that we need to set the size of the mesh. In this case we use this size for demonstrations. Okay, so we have chosen to divide the length of the plate to 50 elements. Okay, this is important later on. Okay, finish now. And then I want to create the mesh, and this is also important step. We need to define the correct elements that is going to be simulated. Okay. Okay, now we're going to see how to use a Python code to run and create elements and on the x direction. This is the equation that are going to be used from Goldak's model, okay, to calculate the body heat flux. Okay, the Q is the welding power, depends on eta, the source heat efficiency, V, the voltage, and E, the current. Okay, as you can see, the voltage is set as 50 volts, amperage is, the current is at 70 amps, and the source heat efficiency for this example is 0.8. Now, this equation also depends on certain constants, the A, B, and C, F. These constants can be found in details in the Goldak's paper. For this example, we're going to show how we choose the A, B, and C. Okay, in order to do so, we need to go back to the model. Okay, now I'm going to explain how to figure out the A, B, and C constants. Okay, you need to go back to meshing and see, first of all, we need to see the welding zone. Okay, the welding zone is represented by two lines of elements. Okay, let me select elements. Okay, so the welding is going to happen in these two elements. Okay, so the A and B and C depends on this element sizing. Okay, as we have said before that the origin or the reference must be located in this place, is defined by a single element. So ABC is the dimension of the element size. So the A is the radius from 0 to the end of the element. And if we like here, the element size is 2 millimeters. So let's check the element size along Y direction. So the A is the element size along the Y direction. Okay, you can see here is 2 millimeter. Now the same thing goes for the B. The B is the element size along Z direction. Okay, Z direction, and can be explained in this place because the sets are going to be selected by a bounding box by the coordinates x, y, and z. So let me change the view. Okay, here we go, the z direction. So the element size along z direction, okay, so the first element now is 1 millimeter. Okay, this is important, and you can change the element size if you want, but you need to make sure that is matches the same element size in the files, in the Bitton file. So now the CF constant, okay, it's defined in files, and it's supposed to be the same, okay, the same as A, okay, can be larger, okay. For this example, we're going to keep it as A, so we have like a circle, so to speak. Now let's check. Okay, this is important now to understand the number of elements along X must also be the same as here. So this is also important because the element size along X is automatically calculated. So it's 2 millimeters, and it depends on this number. So this 50 elements in the mesh must be the same in file, or in file must be the same number of meshing used in the mesh step. Okay, now what is left is the time, is welding time. So the welding time in this example is 50 seconds. If you want to change that number, you need also to define it in the model and in the file. So 50 seconds must be defined here and also in step in here. Okay, if you want to change the time, you can change it here, but also make sure that t variable in the file must be the same. Okay, now for some of you that have directly the welding speed, okay, is you need to simply extract the time. Okay, you can use this equation to extract the time and put it in the file and in the model. That's it. Okay, so we're now going to run this Bitton code. Okay, make sure the extension is correct. Now you can see that first we have created sets from 1 to 50 sets. Each set contain 2 elements. Okay, this is can be changed. Okay, if you want to refine the mesh, it can include more elements. This also depends on the width of the welding. Okay, so now we have the amplitude control when the load is applied. First, it's from 0 to 1 second. We have the max amplitude applied. Then it's going to be 0. For the second amplitude, it starts 0. Then from 1 to 2 seconds is going to be max, and then we need to make sure that is 0 again, and the same goes for the 49 second and so on. Okay, this timeline is important for applying the loads. Here you can see that the load is defined automatically as amplitude 1, and the value for the load is calculated using the correct dimensions. Finally, we run the simulation. After the simulation is completed, now we're going to check the results. The first result is going to be the nodal temperature that is applied from the heat flux. Okay, you can see the welding torch and the impact of the temperature on the plate. Here we can see the stress or mistress. If you want to check also the residual stress,